So chapter 5 is titled Nomenclature. And nomenclature means a system of naming. And so we're going to talk about how chemicals are named. There are different categories of compounds. So just like we've classified matter, we classify compounds based on what they're made up of. And each class of compounds has a different system of being named. That happens a little bit with the human population. My ancestors came from Sweden, and they don't do this anymore, but they used to do, what they used to do is they would take the father's first name, and they would add the word son afterwards, and that would be the son's last name. So if your father was John, then your last name is Johnson, if you're a guy. If you're a girl, your name would be John's daughter. And if your father was Carl, you'd be Carlson or Carl's daughter. And so the names, the last names changed every generation, but it was related to your father's name. Okay, most countries don't do that. Some countries, they put the surname, the family name first, and your given name last. In some countries, there are only a handful of family names, and so I think the Koreans do that. There's a lot of Kims, because that's a very common last name. And so people have different ways of naming themselves, and chemicals do too. And so what we need to do is we have to be able to recognize what group is this particular compound in, so that I can apply the right kind of rules for it. So we have binary compounds. Binary means two. So a binary compound is composed of two elements. Exactly two, not three, two. Two elements. And among those binary compounds, we can look at binary ionic compounds and binary covalent compounds. A binary ionic compound has ions in it. And we can identify them because they will have a metal element and a non-metal element. The metals on the periodic table are on the left side. We talked about that. And the non-metals are on the right side. In a binary covalent compound, you'll have two non-metals. So we can look at the compound and put it in one of these groups. So binary compounds that are ionic have cations and anions. So they have a metal and a non-metal. And then this category is broken down into two more categories as well, type 1 and type 2. Well, what does that mean? Well, the type 1 compounds, the metal can form only one cation. And so that's going to include the metals in group 1, which all form +1 ions, and group 2 that form +2 ions, and group 3 that form +3 ions. The transition metals here in the middle can form more than one kind of ion. Iron can be +2 or +3. So a compound containing iron would fall into this category of type 2 compounds. That's if the metal present can form two or more cations. Those cations are going to have different charges. And most of the transition metals will do that. So here are some of the simple cations and anions. If we look here, we see that all of these cations, remember cations are positive, all the cations except for hydrogen are metals. Hydrogen's got to be an exception. He's the baby brother. He's got to break all the rules. So hydrogen can form a cation. The others of these, here we've got lithium, sodium, potassium, cesium. If you look at the periodic table, those guys are all in group 1, and they all have a +1 charge. Beryllium, magnesium, calcium, barium, those are all in group 2. They all form a +2 charge. We can predict the charge that these metals have by looking at the periodic table. And then we have aluminum. Here's aluminum. Aluminum is in group 3. It forms a +3 charge. So the periodic table tells us what the charge is. And then there's a couple of squirrely guys, zinc and silver. Here's zinc and silver. Zinc and silver are transition metals, but they happen to only form one kind of cation. Zinc always forms a +2 cation, and silver always forms a +1 cation. And so we just kind of have to memorize those. And one way to remember that is if you look at aluminum, aluminum is 3+, and then pretend you're going down the steps. You're going down a set of stairs, because this is a grid, and this kind of looks like stairs. Aluminum, and you go down 1, what's 1 less than 2? I'm sorry, 1 less than 3, 2. So zinc is 2+, and then you go down one more step, and silver is 1 less, it's +1. So that can help you remember those guys. The anions, we've got hydrogen. Some periodic tables show hydrogen both in group 1 and in group 7 because it acts like both. Not at the same time, but it can act like either one. So these group 7 elements all form -1 charges. We can remember that by pretending we're playing a board game and you're starting with your piece on the noble gas and you're counting backwards. So bromine's -1. So we've got hydrogen, fluorine, chlorine, bromine, iodine, all form -1 ions. And then going over one more, we've got oxygen and sulfur. A trip on my cord there. We've also talked about how when we name these anions, we change the ending of the name. So chlorine becomes chloride. So those are the names of most of the simple cations and anions. So how do we name a compound? Well, we always put the cation first and the anion second. Like I told you, I think of metals as being masculine and nonmetals as feminine. And so when you address a wedding invitation, it's always Mr. and Mrs. You put the man's name first. So in these compounds, you put the metal name first. So the metals first, the cation, and the anion second. A simple cation takes its name from the element. So we're talking about type 1 compounds right now. These are compounds where the metal only forms one ion. So here we have AlCl3. In the formula, the metal is first, and in the name, the metal is first. The ion present here is Al3+, and its name is just aluminum. And then we name the anion. The anion is named by taking the element name and changing the ending to -ide. Just like, traditionally a woman changes her last name. These nonmetals, I think of them as being feminine, and so they change their names. So we end up with the name aluminum chloride. Let me write that out because it's not actually written out anywhere here. So the name of that compound is aluminum chloride, and those are separated. Most of the compounds we're going to encounter have 2 names, just like most people that you run into go by 2 names. There are a few that have 2 first names or 2 last names or hyphens or something, but mostly it's, a first name and a last name, and the compounds are going to do that too. Any questions about that one? Let's do some examples. So here we have a compound, and it's got 2 elements. We can tell that because there's 2 capital letters. So even though we've only talked about one kind of compound, we're still going to practice identifying them, because that's the first step. What category does this belong to? What country is this person from? How should we name him or her? So there's 2 elements. And then we look at the first one. Oops, keep doing that. We look at the first one, potassium. Find it on the periodic table. Is it a metal or a nonmetal? It's a metal. It's way over there on the left. It's in group 1. The group 1 elements always form one ion. And so we name that ion, and it's just potassium. At least today's going better than Monday did. Potassium. And then what's the other part? Chlorine. That's the nonmetal. But we don't write chlorine because this is an ion. We change the ending of the name to chloride. So this is potassium chloride. We use a lot of prefixes and suffixes in chemistry, well, in science in general. Let's look at this next one. MgBr2. The 2 is telling us there are 2 bromine ions, but what we're concerned about with is that there are 2 different elements. There's magnesium and there's bromine. 2 elements. Find magnesium on the periodic table. Is it a metal? Yes, it is. So then we have a type 1 ionic compound because magnesium is in group 2. It always forms a +2 ion. So we name the cation first. It's magnesium. And this is where knowing those element names and symbols is going to save you a lot of time. And then bromine, Br stands for bromine, so we change its name to bromide. And that is magnesium bromide. And here's the third one, CaO. 2 capital letters, that tells us 2 elements. Find Ca on the periodic table. Is it a metal? It is. It's way over on the left side. It's in group 2. Group 1, 2, and 3 always form predictable ions. They only form 1 ion. And then those 2 funny guys, zinc and silver. So we just name this the same as its element, calcium. And O stands for oxygen. It's an ion. And so we change the ending. Oxygen becomes oxide. And you might say, well, that's not really just changing the ending. Why isn't it oxygide? I think the giggle is enough reason for that. It is dumb. That sounds crazy. It's not oxygide. It's oxide. So there are patterns, but just like with the English language, you know, I before E, except after C, right? So there are some exceptions. Any questions? Yes? Why don't we say magnesium dibromide? That's a good question. There are compounds where we use prefixes like di to say. So why isn't this magnesium dibromide? We don't need the di to tell us how many bromine ions there are because magnesium is 2+ and bromide is -1. And so we know from the charges that there will be 2 bromides. And so then we're not going to put it in the name. So the way I view, you know, I wasn't there when they came up with this stuff, but the pattern I see is that we don't write unnecessary stuff. We write the very minimum that will communicate what we need to communicate. There is another group of compounds, it's the binary covalent compounds. They don't have charges. And there we do need prefixes to tell us how many of each atom there are, but we do not use prefixes with ionic compounds. That was a very good question. Any other questions? So what is the name of this compound, SrBr2? Well, what's Sr? Strontium. So we could eliminate B then, right? Because it's not sulfur. Strontium, and we know that Br is bromine, but this is an ionic compound, isn't it? Strontium's a metal. It's way on the left side of the periodic table. This is a metal, and so bromine has to change its name to bromide, so A isn't going to work. And C has a prefix in here. We don't need that prefix. And so that's not the correct answer. The correct answer is D. Sometimes when you're doing multiple choice, it's helpful to just eliminate things that you know are wrong. Sometimes it's helpful to not look at the choices at all because they can confuse you. So, you know, some test-taking strategies. So we said the binary ionic, I almost said bionic, binary ionic compounds, there were two groups, type 1 and type 2. Type 2 is where the metal can form more than one charge. So as an example, we've got, I don't know why this picture is in here, that's kind of dumb. So here we have iron as a transition metal. Iron forms two different ions. It forms Fe2+ and Fe3+. You can't tell that by looking at the periodic table. These transition elements are just not very predictable. Since there are two possibilities, we need to specify which one is in the compound that we're naming. And we do this by using Roman numerals. So the Roman numeral is going to be used to indicate the charge. The transition metals are the ones that usually require a Roman numeral. Well, that's too fat. Here's Al. Can you see that at all? There's Al, here is zinc, and here is silver. So zinc and silver are the two exceptions we are going to learn about in the transition metals that do not need Roman numerals. They don't use a Roman numeral because their charge is predictable. It's always the same. Aluminum is 3+, we know that because it's in group 3. Zinc is 2+, and silver is 1+. And I already showed you how this is just going down the steps. 3, 2, 1. So those are transition metals that don't need a Roman numeral. So here are some of the more common type 2 cations. So we see that iron has +3 and +2 charges. So iron with a +3 charge is named as iron with the Roman numeral 3 in parentheses. And iron 2 is iron with the Roman numeral 2 in parentheses. The Roman numeral tells us the charge on the ion. It does not tell us how many of those ions are there. It just tells us the charge. And just in case you're a little rusty on Roman numerals, 1, 2, 3, 4, 5, 6. We'll never get past 7. So the Roman numeral 1 is a capital I. The Roman numeral 2 is 2 capital I's. The Roman numeral 3 is 3 capital I's. Okay, you can't just go on like this indefinitely, right? Because 25, you can have 25 capital I's. That's not going to be real useful. So they do use some other letters. Capital V is 5. 4 is 1 before 5. So the Roman numeral 4 is the Roman numeral for 1 before the Roman numeral for 5. It's 1 less than 5. 6 is 1 more than 5. And 7 is 2 more than 5. Aren't you glad you don't have to do math with Roman numerals? So when we look at these guys here, tin can form a +4 and a +2. So tin 4 and tin 2. When we read these, when we pronounce them, we use the English name for that number. So that would be tin 4 and tin 2. And here's lead 4 and lead 2. So these are the systematic names, and these are the names that we're going to use in this class. There's an older system of naming which used suffixes and the Latin names. And so there was ferric and ferrous, cupric and cuprous, stannic and stannous. But the ick and the us did not mean a particular number. They just meant the higher one and the lower one. And so you still had to know that tin was either 4 or 2, and iron was 3 or 2. And so I'm going to tell you that this exists, but we're not going to do it, because that's too hard. We're just going to use this method. One little weird guy here, which we will avoid using because he's just not that common and he's annoying. Mercury 1. We would expect that that would be Hg with a +1 charge. but it isn't. It's two mercury ions together, and together they have a +2 charge. So it's out there, we're not going to talk about it anymore. So when we name these type 2 ionic compounds, it's the same idea. We name the cation first and then the anion. But because the cation can have more than one charge, we have to indicate what the charge is, and we do that in parentheses with the Roman numeral. Okay, so here's an example. So Fe2O3, we're going to name this guy. So first we look and we ask ourselves, how many elements? 2, iron and oxygen. And then we ask ourselves, well, is iron a metal? Well, we don't even have to look at the periodic table for that. We know that iron is a metal. But we do need to find iron on the periodic table so that we can tell, does it form just one kind of ion, or does it form more than one? Well, it's in the middle there, isn't it? The ones that form one ion are groups 1, 2, 3, zinc, and silver. Everybody else needs a Roman numeral. So if it's not in groups 1, 2, or 3, plus zinc and silver, it needs a Roman numeral. So we know that we need a Roman numeral for this guy. The Roman numeral is the charge. We need to know what its charge is. Can we tell real fast just by looking at this what its charge is? No. We have to figure it out. Once you practice figuring it out, you'll be able to see it much easier. To figure it out, we're going to have to look at the charge on the anion. The anion charges are very predictable. Oxygen. Oxygen is in group 6. So if we start with the noble gases, we count back -1, -2. Oxygen has a -2 charge. So here we have oxygen with a -2 charge. And we know that there's 3 oxygens and there's 2 irons, and together their charges add up to 0. So your book here gives a little more of a mathematical way of looking at what is the charge on the iron, but you might prefer to, draw pictures. So here's O2 minus, and the formula shows us that we have 3 of them. So I'm going to draw 3 of those. So if I have 3 of those guys, my total negative charge is going to be 6, right? Each of them is -2, and there's 3 of them. And then the formula tells me that there's 2 irons. So I've got 2 and 2. I'm sorry, 1 and 1 is 2. I have 2 iron ions. Well, the charge over here has to equal +6. Why? Because the charges add up to 0. Compounds are neutral. The ions combine in a way that overall the charge is neutral. So because we know that the total negative charge is -6 based on our knowledge of the charge on each oxide ion and how many there are, we know there's a total of -6. That means there must be a total of +6 charge also. The +6 charge is going to come from these 2 iron ions. So we've got 6 cookies, and we're trying to share them between these 2 little boys. And it's important with little children that they're equal, right? It has to be equal. The cookies even have to be exactly the same size. If you have children or remember being a child, you remember that that's really important. So I've got +6 here. I'm trying to share it between these 2 ions. What are they going to get? They each get 3. Okay, this is not hard math. The block people have is just thinking about it. But if you can divide 6 cookies among 2 boys, you can figure out the charge on the iron ions. So that means these must each be 3+. So 3, that's the name. So that's where this comes from over here, iron 3. And then the anion is named oxide, and so I'm going to write the full name up here. Iron. There's no space between the word iron and the parentheses. Iron 3, and then there's a space, oxide. So we don't find the charge on the cation from the periodic table, we find it from the anion. Any questions? Let's do some more examples. So we look at the compound we're supposed to name and we ask ourselves how many elements. This is 2 elements. It's got Cu and Br. Then let's find Cu on the periodic table. It's on the left side. It's a metal. Okay, so we've got a binary ionic compound. Is Cu in group 1, 2, 3 zinc or silver? No, it isn't. So it needs a Roman numeral. So its name is going to be copper with some Roman numeral, and then bromine is bromide. So we can kind of sketch out what the name is without completely finishing it. Bromine becomes bromide. We got the Roman numeral there because it's not in group 1, 2, 3 zinc or silver. Well, now we have to figure out the charge. Well, we have 2 ions here. We've got bromine and we've got copper. What's the charge on bromide ion? Look at the periodic table. It's -1. Because we always start in the far right column, those noble gases are 0, you count backwards, -1. So bromide is -1, and there's 1 bromide and 1 copper ion. They have to add up to 0, so copper must be what? +1. +1. That tells us that the Roman numeral here in our parentheses is the number 1. So it's copper 1 bromide. We don't include the Roman numerals with the type 1 because it's not needed. I think students would probably prefer that we just do it on everything and be consistent that way, but we're trying not to write things that we don't actually need to write. How about FeS? 2 elements. One's a metal, one's a nonmetal. And we find Fe on the periodic table and ask ourselves, does it need a Roman numeral? It does. Okay, so its name is going to take this form, iron something, and S stands for sulfur. Sulfur becomes sulfide. Now we have to look at the charges to figure out what the charge on the iron is. So we've got 2 ions here. We just got 1 of each. What's the charge on sulfide? -2. We find it in the periodic table. We count -1 to chlorine, -2 to sulfide. We have 1 iron and 1 sulfur. The sulfur's -2. The iron must be +2, right? So this is Fe2+. That tells us that the Roman numeral is 2. The Roman numeral tells us the charge on the ion, not the number of them. It's the charge. How about PbO2? 2 elements, right? First element's a metal. Well, we find it on the periodic table. Well, it's over here in group 4. It's not a transition element, technically. But what about the rule, group 1, 2, 3, zinc or silver? Is that in group 1, 2, 3, zinc or silver? No, it needs a Roman numeral. So Pb is lead. So this is going to be lead with a Roman numeral. We'll leave a space there. And oxygen is oxide. gotta stop getting myself trapped over there. So we need to look at the charges here. Now this one's a little more complicated. It's not just one of each. So we've got one lead ion and two oxygen ions. And each of the oxygen ions has a charge of what? -2. So there's -2, and this one has a -2. And when we add those up, we get -4. If we've got -4, the total over here must be +4. There's only one over here, so it must be +4. So then it's lead 4 oxide. Any questions? What's the name of this compound? CrO2. Well, we've got Cr, which is chromium, and O is oxide. Does chromium need a Roman numeral? It does. So that tells us that two of these are flat out wrong, right? A is wrong, there's no Roman numeral. B is wrong, D is wrong. The prefix is nice. I would know what you mean, but that's not how we say it. So then we're left with chromium 2 oxide or chromium 4 oxide. Well, let's look at these guys. So we've got 2 oxygens. And we're just going to total things up a little bit here. Each oxygen is -2. We can figure that out from the periodic table. There's 2 of them. That gives us a total of -4. Then over here the chromium must be a +4. Total, there's only 1, so this is 4+. So it must be letter C. Now, drawing these little symbols and adding them up and stuff, do that on paper if you need to, or do it in your head if you need to, or some of you can just look at it and see. It has to do with least common multiples and those sorts of ideas from math. But pictures work too. Here's another one.